components of a vector in 2D. 2D. Now in 2D, okay, a vector can be represented along x and y, along x and y. So if we have vector A, okay, between the x and the y-axis, it's known that this is, let's say, making a shadow on the x-axis if a light is just on it, and it's making a shadow on the y-axis, so that the part under the shadow, okay, now this is said to be the x component of the vector, and this is the y component of the vector, so that this is ax and this is ay. Now in 2D, the vector A is represented as ax along the I and ay along the j. So if the vector is between the x and the y-axis, it's making angle, okay, an angle theta from the positive x-axis, or the y. So from trigonometry, we do have this sine is equal to sine theta is equal to opposite over hypotenuse. Now in our case here, the opposite is ay, so that sine theta is equal to the opposite is ay, and the hypotenuse is the magnitude of a or a, implying that ay is equal to a sine theta, magnitude of a sine theta. In the same manner, cosine of theta is equal to adjacent over hypotenuse. Now this is equal to the adjacent for this angle is ax, and the hypotenuse is again the magnitude of a or a. Then ax is equal to magnitude of a cos theta. Then now vector A can be expressed in terms of a along xi, okay, plus ay along j. Now this is to mean a is a sine theta, okay. Now ax is a cos theta, okay, cos theta along I, plus this one is a sine theta along j. This is how we represent a vector, okay. These are the components of the vector. But here, sometimes we may be supposed to determine the angle which it makes with either the positive x-axis or the y-axis. In our case, here we have a third trigonometric function, which is the tangent. So tan theta is equal to sine theta over cosine theta. And we know that sine theta is opposite over hypotenuse, divided by cosine theta is adjacent over hypotenuse. This provides opposite over hypotenuse times hypotenuse, okay. We took the reciprocal of this hypotenuse divided by the adjacent, okay. So that tan theta is equal to opposite over adjacent of our coordinate system. Then from this theta can be written as tan inverse of opposite over adjacent. So in our case, the opposite is, now this is equal to tan inverse. The opposite is ay, and the adjacent is ax. So that the angle theta, the direction of this vector, is given as tan inverse of ay divided by ax. Ay divided by ax. So this is how we resolve a vector into its x and y components in 2D. Let's see a few examples about this. Okay, here we have an example. Calculate the components of the force shown below. Now in the xy plane, a 20 Newton force, a 20 kilonewton force is making an angle of 30 degrees with the x-axis, which means this force has x component, okay, x component, which is equivalent to this, okay, force along x, and y component, which is equivalent to this. This is force along y. Force along y. Now we are supposed to find the components of this force, meaning the force along x and force along y. From our previous discussion, we know that this force is equal to force along the x in the direction of I plus force along the y in the direction of j. We discussed that force along x is force cosine of theta along I plus force sine of theta along j. Now this is the x component and this is the y component. So that Fx, okay, force along x is equal to F is 20 kilonewton, 20 times cosine of 30 degree. 20 times cosine of 30 degree. Now the cosine of 30, this is 20 kilonewton times the cosine of 30 degree is 0.866. This goes to, this is 2 times 8.66, okay? 12 carry 1, 13 carry 1, 16, 17. Okay, Fx is equal to 17 kilonewton. In the same manner, Fy, which is equal to F sine theta. Then F is 20 kilonewton, and sine of 30 degree is 0.5. This is equal to 10 kilonewton. So the force is resolved, okay? This force is resolved into F and Y, okay? X and Y as a force. Force X is 17.32 kilonewton, and Fy is equal to 10 kilonewton. So the force which had been 20 kilonewton can be resolved as 17.32 kilonewton along I plus 10 kilonewton along J. This is how we resolve a force into its components. So that this is a 10 kilonewton magnitude vertical force, and this is a 17.32 kilonewton horizontal force, which had been the components of a 20 kilonewton force, making an angle of 30 degrees from the horizontal. We have another example which says determine the magnitude and direction of the resultant vector whose x and y components are shown below. Here in the xy plane, in the xy plane, 6 units of x component is shown, and 8 units of y component is shown. So we are asked to find the magnitude and direction of the resultant, magnitude and direction of the resultant vector. Since we do have 6 units in the positive x-axis and 8 units in the positive y-axis, along the positive y-axis, the most probable location of the resultant vector is between the two, okay, between the two, so that this is the resultant vector. Now, according to our previous discussion, the resultant vector r, the magnitude of the resultant vector r, is equal to the square root of let's say the vector along x. Okay, let's say vector along x square, magnitude of vector along x square, plus vector along y square. Here we have the x component 8 units. Here we have the y component, the x component. So that this is equal to the x component is 6 square, plus the y is 8 square. This is going to be 36 plus 64, which is 100. So the resultant has length of 10 units, or magnitude of 10 units. This is 10 units. Okay, 10 units. Good. As we locate the resultant between the x and the y-axis, there is some angle that this resultant makes from the positive x-axis. That angle is said to be direction of the resultant. So to find the direction of the resultant, we can use one of the trigonometric functions, sine, cosine, and tan. But the better way is to determine the tangent. Okay. Now tangent of theta is equal to opposite over adjacent. This is equal to, the opposite is 8 and the adjacent is 6. So that this implies theta is equal to tan inverse of 8 over 6. Now tan inverse of 8 over 6 is around 53.1 degree. Okay, 53.1 degree. So that the direction of the direction of the resultant vector is 53 degree from 53 degree counterclockwise from positive x-axis. Okay, this is counterclockwise from the positive x-axis. So if this is so, we can have further example. This is example 3. Now it says calculate the magnitude of the component forces. Okay, the component forces. The magnitude of the component forces of the resultant. Okay, the resultant force. Okay, the magnitude of the resultant force, the direction of the resultant force from positive x-axis. Now here we have 4 different forces. Force of 10 kilonewton acting 30 degree above the x-axis. A force of 12 kilonewton, okay, the second force acting 53 degree from the positive x-axis. And here we have a third force, okay, acting a 6 kilonewton force acting along the y-axis. And here we have force which is acting 135 degrees from the positive x-axis. All angles are measured counterclockwise. So to see how we do, okay, we have to put each force individually in our imagination, so that F1 is 10 kilonewton. Now it's making 30 degree from this. Then we should think of resolving this into F1x and F1y. Okay, we simply resolve this force into F1x and F1y. Again, we should do the same for force 2, which is 12 kilonewton, and this is making an angle of 53 degree from the horizontal, okay, from the horizontal, so that we should resolve F2 into F2x and F2y. The same has to be true. The same is true for the third and the fourth force. But to do this, it's better to keep all we have in table 4, so that here we have component. Let's say force vector, force, okay, x component, y component, okay, component. Then having this will help us to add up all the x's, all the y's to find the resultant force. Now the force is F1. The magnitude is 10 kilonewton. So that F1x is equal to F1 cosine of 30 degree. This is equal to F1 is 10 kilonewton times cosine of 30 degree is 0.866. This is equivalent to 8.66 kilonewton along the positive x-axis. So that this is positive 8.66 kilonewton, x component in kilonewton, y component in kilonewton. Okay, positive 8.66 kilonewton. Now Fy is equal to F1 sine theta. F1 is 10 kilonewton, sine theta is 0.5, so that this is 5 kilonewton, again in the positive y direction. So this is positive 5 kilonewton. Now for the case of F2x, okay, F2 along x is equal to F2 cos 53 degree. Now this is equal to F2 is 12 kilonewton, cosine of 53 is 0.6, I think, 0.6. 0.6, so that this is about 72 to 12 to 7.2 kilonewton. 7.2 kilonewton. Still, this is in the positive direction, so that for force 2, which is 12 kilonewton in magnitude, has an x component of 7.2 kilonewton. And the y for this is F2y. F2y is equal to F2 sine of 53 degree, because this is equivalent to the y component of this vector, so that F2 is again 12. The sign of this is 0.8. Then this gives 18 carry 1, 9.8 kilonewton. Still in the positive direction. Positive 9.8 kilonewton. Okay, kilonewton is written. Okay. Now the third force, F3, the force is 6 kilonewton, 6 kilonewton, 6 kilonewton. Now this 6 kilonewton is simply line. Okay, it's along the y-axis. So its contribution or its component along the x is, okay, this is 6 kilonewton, which is F3. Okay, if it's in the y direction, it's making an angle of 90 degree, so that F3x is equal to F3 times cosine of 90 degree. Cosine of 90 degree is 0, then F3x is 0. F3x is 0. Now F3y is equal to actually it's exactly on the y-axis, but F3 times sine of 90 degree. Sine of 90 degree is 1, so that 6 kilonewton times 1 is 6 kilonewton. Okay, this is along the positive 6 kilonewton. Okay, 6.0 kilonewton. Now here we have the force. Okay, F4. Now F4 is making an angle of 135 degree. Okay, this is making an angle of 135 degree. 35 degree from the positive x-axis. Okay, positive x-axis, and sorry, this is F4. F4 is making 135 degrees, kilonewton. Okay, now logically, the y component of this, okay, this is raising. The y component of this is positive, and the x component of this is negative. But in the obvious mathematics, okay, now here we have this is f for x, and this is f for y. Now f for x is equal to f4 cosine of 135 degrees. Now this is equal to 18 kilonewton times cosine of this is negative 0.707. Okay, now the product goes negative, this is negative 12.73 kilonewton. Now force 4, which is 18 kilonewton, has an x component of negative 12.73 kilonewton, and the y component for this is f4 y is equal to f4 sine 135 degree. This is equal to 18 times 100. So sine of 100. This is 0. Sine of 135, 0.707. Okay. This is equivalent to 12.73 kilonewton. Positive 12.73 kilonewton. Okay, kilonewton. Now we have finished the components. The components for each vector. Okay, the components for each vector. Then the next step is adding up each component to find the resultant. Okay, now here we have the resultant vector. the resultant force or the resultant vector, then the components of the resultants are, okay, the components of the resultants are the sum of the x's and the sum of the y's in this table. So the first is 8.66, okay, plus 7.2, okay, this is equal to minus 12.73. Along x, we do have positive 3.13 kilonewton. Along y, this is positive 5 plus 9.8 plus 6 plus 12.73. This is 33.53 kilonewton. So the resultant vector can be represented as, can be simply represented as a vector having, or a force having this component of x and y. Now here we have r. Now both are positive, okay, both are positive. Y is positive in this quadrant, x is positive in this quadrant, so the resultant is laying here, okay, laying here in this one. Okay, now r, whose x component is very short, and whose y component is comparatively, let's say, long. Now, so that this is about the x component is about 3.13, and the y component is 33.53. Okay, so this is the resultant vector. Okay, this is the resultant vector. So the magnitude of the resultant is the magnitude of r. Is equal to the square root of the magnitude of rx square plus the magnitude of ry square. This is equal to, okay, this is equal to the square root of 3.13 square plus 33.53 square. Okay, 3.13 square plus 33.53 square. This is equal to the square root of 1134.1. Square root of 1134.1. This is equal to 33.68 kilonewton. This is the magnitude of the resultant. The magnitude of the resultant is equal to 33.68 kilonewton. 33.68 kilonewton. Now, the magnitude of the resultant force is 33.68 kilonewton. Now, the magnitude of the component forces along x and along y, okay? Along x, it's positive 3.13. Along y, this is equal to 33.53. Now the next is calculating the direction of the resultant force. Here we have theta, tan theta, tangent tan theta, this is 3, tan theta is equal to opposite over hypotenuse, then theta is equal to tan inverse tan inverse, opposite over opposite over adjacent, adjacent, opposite over adjacent. Okay, tan inverse of opposite over adjacent. This is equal to tan inverse of the opposite is 33.53 and the adjacent is 3.13. Now 33.53 is equal to divided by 3.13. This is 10.7. Tan inverse 10.7. Now shift tan 10.7 is equal to 84.7 degree from the positive. Okay, this is equal to 84.7 degree. 84.7 degree. This is equal to 84.7 degrees. So this is how we resolve the components and find the resultant in a 2D in a two-dimensional component of vector. Next time we'll see the three-dimensional vectors, and this is HATU. Okay, HATU. I hope you said aha after seeing this, because some of the big matters are being resolved here. Like and share HATU so that we'll keep on helping you. Thank you very much.